Okay, fantastic. So, first of all, I'd like to canonically thank Alessandro and the organizers for setting up this meeting. And I really hope it's a good sign that in spite of the boundary conditions, we can still have it. And very much I would like to thank them as well for giving me the opportunity to present my work. And today, given the spirit of the conference, what I would like to discuss is what we can learn from integrability in this kind of work, project, long-term project that I've been working on in the last years, which concerns the study of quantum field theories in general in the special sectors of large quantum number or large charge in particular. So if you want to know what to read about these things, this is the original paper 5 years ago when we started everything. But in fact, it's much, much better to look at the review that we published a month and a half ago by now, because in the meantime, our understanding of these things has improved a lot, I think, and I hope we're much more clear in this review here. While today I will mainly discuss results that come from work of 2 years ago here and in May this year, which are more related to the issues of integrability. So before I get started with the actual work, I'd like to introduce you my friends. So these are the people with whom I've been working on this project, and as you see, we're pretty much geographically delocalized. And just in geographical order, east to west, this is Simeon Hellerman at the University of Tokyo. This is Masataka Watanabe at Weizmann, Francesco Sannino, who's in Denmark, Susanne Reffert in Bern, Debashish Banerjee in Berlin, Luis Alvarez Gomez at the Simon Center in Stony Brook, and this is Shailesh Chandrasekaran at Duke University. So what am I going to talk about today? The main interest of today's talk will be conformal field theories. Well, I will concentrate on superconformal field theories because it's there that we see integrability, but more in general, our approach is tailored really for conformal field theories. And they are important for a number of general reasons. For example, because you see them everywhere. Generically, if you study the RG flow of a given QFT, you will expect at the endpoints of the RG flow to find a conformal field theory. And they're very interesting from the phenomenological point of view, because essentially for this reason, they describe critical phenomena. In particular, this one is just a shot taken from a video you can find on YouTube of what happens to helium-4 at the superfluid transition. It's actually very, very funny to look at all sorts of things that happen when you have a superfluid. And as we all know here, the really conformal field theories are the only way we have, as we've seen from the previous talk, to understand anything at all about quantum gravity via the ADS-CFT correspondence. And even more in general, you know, the very fact that string theory exists is because at heart, again, as we've seen from the previous talk, it's a two-dimensional conformal field theory. That's the only way we have to actually do computation that go beyond the usual, in a way. But okay, today I don't want to talk about these complicated things. I want to have more a general approach for the beginning, at least, so to tell you why we're working on these things. And the main problem when we look at conformal field theories is that as much as they are important, as much as they are ubiquitous, they're actually complicated. And the reason why they're complicated is that a generic conformal field theory, a natural conformal field theory in the technical sense, will not have small parameters. And unless you have integrability, as we know here, well, the only thing we know how to do normally in physics is perturbative computations. But a generic conformal field theory will not have some small parameter to use for computations. Now, our observation is very simple, that if you don't have just a generic CFT, but you have a CFT that has some symmetry, you can make use of it And if you're lucky, if under certain assumptions, using the symmetry, you can still try to construct something that looks like a perturbative expansion. So if you really only want to keep one message from today's talk, is that what you can do if you have a CFT or a QFT in general that has a global symmetry, is that you can break the Hilbert space into sectors of fixed charge, just because it's a symmetry. And under certain assumptions, what happens is that in each of these sectors, you can write an effective field theory in which the charge that is associated to that sector acts as a controlling parameter in a perturbative expansion. So your theory has no small parameters, and then you give yourself a small parameter. Okay, so I'm talking about CFTs and talking about symmetries. I'm sure you expect me to say bootstrap. So there you are. This is not bootstrap. And this is not bootstrap in a very precise sense. So first of all, technically, we're really writing effective actions. We are not writing consistency conditions. We really, just Lagrangian. We're really writing Lagrangians for CFTs. And in another sense, it's orthogonal, because the sectors of the theory that in general we know how to access, unless there is integrability, today things change a little bit, are different from those that are usually accessible via bootstrap. So we study different parts of the theory. It is complicated to relate our results to the results of bootstrap. And, well, little caveat, there was a very beautiful paper 3 years ago now, by Zhiboidov and Jaferis, where they showed that the predictions of large charge actually have a correspondence in some bootstrap construction. But anyway, so these are words, but concretely, what can I do? What is the result? The result is, the first result we found is this thing, which concerns the study of the ON vector model. The very simple Wilson-Fisher fixed point, the theory that you study when you're in university, okay? And it's extremely studied, it's extremely useful. It is actually useful phenomenologically, but it's complicated. It is complicated because I'm really talking about ON for small n, and really talking about ON in 3 dimensions. So you cannot do 4 minus epsilon, you cannot do large n, and it's complicated to get anything explicit. So for this model, what I'm telling you is that you can write an asymptotic expansion in the charge for the dimension of the lowest operator of given charge, let's say Q. And what you find is that the conformal dimension of the lowest primary will go like charge to the 3/2, and then there's going to be charge to the 1/2. Then there's going to be a universal number that is n independent. Okay, so I give you this formula, which is very simple. It contains 2 parameters that they are beyond the reach of our approach. And, it seems the kind of thing that people should know about, like in the 70s. But in fact, it turns out that A, there are essentially no known closed results for the ON model. And it's even complicated to check if this is true, in the sense that we have this prediction, and now we would like to compare it to something. But now you have the problem that you don't know how to compute these conformal dimensions otherwise. One thing you can do is to put everything on a lattice. You ask the computer, what is the dimension? Well, it turns out that even this is very complicated. We were very lucky in finding Shailesh and the Bashish that are experts in these computations. So they took the O2 model, they put it on their computers, they had the cluster at DAISY run for days, and then they gave us this. So this plot shows the conformal dimension of the lowest operator in the 3-dimensional O2 model as function of the charge. These blocks here represent the points obtained on the lattice, and these are just big squares because like this you can see them. I usually get asked, I've been already told showing this plot, oh, I can't believe it because you're not showing the error bars. So no, I am showing the error bars. The problem is that the error bars are less than 1 pixel thick. So the error bars are invisible. And you see, the result that I found on the lattice, this is compared to the prediction we had before, this curve that goes like q to the 3/2. I have to fit 2 points because I have two numbers I cannot derive in my model. So one way of looking at this is that this is prediction in the sense that you give me two numbers, any two of these, and I give you 10 numbers out of it. So, well, first time I've seen this curve, actually I couldn't believe it. It works a little bit too well. But maybe you have time to go back to that. Yes? Of course. So the question is if I have an intuitive understanding of why the leading term is 3/2. So yes, and the intuitive understanding comes from the fact that we have a conformal field theory. So when conformal dimensions are actually energies in the precise sense that you can use the state operator correspondence. So when I look at a dimension, it's the same thing as the energy on a sphere. So think that here it says energy. Now, when you think again in terms of the state operator correspondence, you want to put your system on a sphere. So instead of thinking of a charge, you can think of a charge density. Now, dimensionally, energies have dimension 3. Energy densities have dimension 3. Charge densities have dimension 2, just because the charge is an integer and the energy has dimension 1. So, and this is a CFT. It means there's nothing dimension full in your theory. This breaks if you have a lot of supersymmetry, but as long as you have a bosonic model like this one, you are automatically forced to have this. Okay. How do we get there? Well, the idea is to construct a Wilsonian effective action. And then you remember what you teach your students. Oh, how do you do a Wilsonian effective action? You take your theory, you choose a cutoff, and you say, these are higher energy degrees of freedom, these are low energy degrees of freedom, and then you integrate out magically the high energy degrees of freedom, right? And we all know that at this point, all the students go like, yes, 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 that's obviously true. And we also know that it's false. The reason is, if I could really integrate out high energy degrees of freedom, I would just be integrating out the theory. There's no need to do anything effective. So what do you actually really do? Well, what you actually really do is you try to write an effective action looking at the scales of your problem. In particular, what you can do is that via the state operator correspondence, a system on the plane is the same thing as a system on a sphere. So you have a scale in the problem, which is the radius of the sphere. And then you also have, if you look at the system of fixed charge, you have another scale, which is given by the charge density that I was saying before. This means that even if your CFT itself has no scales, if you look at the sector of fixed charge and you consider the state operator correspondence, you really have two dimension-full objects. One is the inverse radius here, and one is the charge density. And then what you can do is that you can try to write an effective theory with a cutoff that is much bigger than this and much smaller than that. You have what people call scale separation, at least if you're in the limit where the charge is very large. And then you know from general arguments that if you write an effective action that works in that sector, automatically you'll have a perturbative expansion where the perturbative control is given by the ratio of the high energy scale to the low energy scale. That's it. Okay? So now you just have to make all of this precise. Of course, this means that a lot of preconceptions that people have about Wilsonian actions, you know, that they are useless, maybe they're just a cute qualitative description, maybe you can use them to organize a perturbative expansion, blah, blah, blah. These are really superstition. You can use the Wilsonian effective actions to actually compute stuff, as long as you know what you're doing. Okay, so let me just make one little comment here. When I told you, when you look at this curve, you should be worried, because it works too well. As I said, everything should work in the limit of large charge, right? On the other hand, you look at the lattice, and everything works also down here. How's that? Does it mean that we're cheating? Well, it's not the first time that this happens, if you really think about it. Another place where this has happened, and we are used to that so much that we don't think about it, is in Regge theory. You see, when you actually see how Regge theory is constructed, you find that m squared goes like j, But this is just a leading order effect. You see, you should put the corrections in 1 over j. Regge trajectories are only valid for j very large. Nonetheless, you go and measure, these are really real experimental results, and you really see the lines going down. So what's happening? Well, what happens is that there's something a bit general that we understand only in part about how unreasonably effective these effective field theories are. Okay, so today, I quickly flashed some results from the EFT for the O2 model in 3 dimensions because it's a very simple model where you still get stuff that is surprising. But I will concentrate on a slightly different problem, which is what we can do when we have, together with the large charge expansion, what we can learn if the system is also supersymmetric, and in particular, if there is enough supersymmetry to have a notion of integrability inside this system. So what do we learn from integrability? What else we can do now? Well, it turns out that, first of all, there is a qualitatively different behavior. This 3/2 is not there anymore because of supersymmetry. But what you can do is that you can compute 3-point functions, and using integrability, you don't just limit yourself to the first 2-3 terms in the expansion. My claim is that you can completely resum the full perturbative expansion using integrability again, and you get results that are so good numerically that you even manage to get a glimpse of what the next saddle in the path integral looks like. So think of it like this, if you want, that what we have done is that we have identified a particular saddle in the path integral of the theory where we can make calculations, and in the supersymmetric case, the calculations are so good that we even managed to see exponential corrections to the saddle. So it's as if we were having, we could see far enough that we see the next saddle in the path integral. Okay, so till now it's been a lot of pictures. From now on I'm going to be much more explicit. I'm going to show formula, so you will see that all of this is not just words, and we can actually compute things. Very good. So what happens when you also have supersymmetry? One thing that changes enormously, because it really changes the physics of the problem, is the following. The ON model in general have isolated vacua. That's it. There's your conformal field theory, it's there. And it is expected, but this is really lore, that this is general unless you have supersymmetry. Once you have supersymmetry in the problem, what can happen is that you have conformal field theories with a moduli space. This is very well known in the case of, for example, of n equal to 4-dimensional field theories, which is what I'm going to study today. And this is true for theory. We know a lot of examples of theories that are also non-Lagrangian. Okay? So it's really theories for which you know the spectrum. You know, these are the Argyres-Douglas theories, essentially. And you know that you cannot write a Lagrangian. It's not like you don't know what's the Lagrangian. It's more that you know that you can't. Okay? And in particular, today, I will concentrate on these theories, taking just a subset of those where the Coulomb branch has a dimension 1. So you have a dimension 1 moduli space, which means that your chiral ring is generated just by one field, one single operator, O, and every chiral operator in the theory is just, well, freely generated by that, so it's just O to the n. And what I want to do is to write an effective action for this field. Notice that it's even complicated to give a perturbative definition of this field in general. For the non-Lagrangian theories, it's not, well, you don't have a Lagrangian, so you don't even know what you're doing. Okay? What I want to do, nonetheless, here is to write an effective action. And just for technical reasons, sometimes I will call it O, sometimes I will call it phi. It's the same thing, just with a different normalization. So let's pretend we know nothing. So we know that, well, what we know is that the physics has to be described just by one chiral field. That's it. How do we write an action for a chiral field? Good. So the first thing is that you say that's a vector multiplet. You need a kinetic term, so you just take phi squared, okay? Which actually means the bosonic part is the usual kinetic term, there are fermions, and there are the gauge field, you know, just the n equals to 2 multiplet. What else? Well, surely you will need a Wetz-Zumino term, because there's going to be an anomaly. You want to write an action in the infrared, it has to match the anomaly in the ultraviolet. If you want to do that, you need to add a Wetz-Zumino term, okay? But here is the power of supersymmetry. The claim is that if you have a supersymmetric theory n equals 2, there are literally only 2 F terms that you can write. There's nothing else. Everything else is D terms. You can write the kinetic term that is here and the Wetz-Zumino term. On top of that, the coefficient in front of the Wetz-Zumino term fixes the anomaly, which means that it's not even a free parameter. This theory has no free parameters. That number, that alpha, is literally the A anomaly of your theory, as it is in the ultraviolet. So you give me a n equals to 2 theory, which has Coulomb branch of dimension 1, you have to tell me what is the A anomaly of this thing, and that has to go here if this effective field theory is to reproduce the same physics. Now, my claim is, a large R charge in this case, this is all you need to know, nothing else, and from here you can construct all the correlators of the theory. So, concretely, what we want to compute, in this case, are 3-point functions. It's because together with the conformal dimensions, they construct, well, they make up all the CFT data of the theory. So what we want to construct are these 3-point functions that in this particular case, since the chiral ring has dimension 1, actually they are equivalent to 2-point function if they were chosen. And these are these numbers here. You see the 3-point coefficients. You can actually, the notation in the literature is they write them as e to the qn, where n is the power that appears here, and the R charge of the operator that you're inserting, or this on, is proportional with a factor that depends only on the theory to the n. So you have these operators, you have n operators living here, n living there, and you want to compute, well, 3-point functions that reduce to 2-point functions. And this is what we want to compute. Once we know these numbers, we know the CFT. We solve the CFT. Okay? Now, I told you we have an effective field theory, which means that in principle, I should be actually able to compute these 2-point functions in a path integral. So, what is a 2-point function? You know, it's really basic. The 2-point function is just given by the insertion of these things here in the path integral, and this is the action that we have written before. Kinetic term, Wetz-Zumino term. Now, n is very large, that's the limit in which we want to work. And what you can do is that you can just exponentiate these insertions as log terms in the Lagrangian. You might be worried that there's something very fishy happening here, because now all of a sudden I have a Lagrangian that contains logarithms. There is nothing fishy about it, because the trick is you're not thinking around phi equal to 0. You're thinking in a sector of fixed charge where phi has a vev. So it's okay. You just have to work. But as long as you're looking, first of all, at the semi-classical state, you can just go on, just compute the minimum of this action, put it back. And what you find is that, first of all, you get the right dependence, this x1 minus x2 here, which is really the 2-point function, because the insertion was in 1 and 2. Well, this thing here tells you that you have the right properties for a CFT. And then what you find is that the leading term, the thing that really governs all the physics, is a q log q term, so that when you compute this qn, which were really the 3-point functions, which is really what you want to know, you find that, well, you have to take a log, but the important thing is that q log q is exactly the leading term that controls everything. We are always working in the limit where n or q, which is equivalent, are large. Okay? Now, this was just the kinetic term. You add the Wetz-Zumino term. You do recomputation again. You find that there's a term here that goes with alpha. But it's finished. What I mean to say is that while usually a Wilsonian effective action has infinite terms, in this particular case, a Wilsonian effective action contains 2 terms. Anything else is forbidden by supersymmetry. which means again that while this is just a semi-classical result, anything else that appears in the quantum computation must be computable as a quantum fluctuation on top of that. In particular, since I am studying what happens around a solution, around a VEV that depends on Q, the loop counting parameter will just become 1 over Q. So this is telling you that out of general principle, the real solution, well, around the asymptotic solution on Q equals to infinity, has to look like this. This is a semi-classical result, and then there is a series in 1 over Q. And the series in 1 over Q, of course, you can compute just with standard techniques. So you just sit down, you start computing loop diagrams, and you make an observation that all the interactions in this theory come from the West-Zumino term. The West-Zumino term comes with alpha, and that's the only thing on which these coefficients here can depend. There's only an alpha dependence, that's it. And then you start computing. So it turns out if you want to compute the leading term here, you have to write these 5 diagrams. And you compute, and you write this thing here. And if you're really good, you recognize that it's a Bernoulli polynomial. But you have to be really good to see that. The more important thing that you see is that everything only depends on alpha. And I remind you, this alpha is the A anomaly, so it's a fixed thing. Good, so now you're super happy. You got the leading behavior, you got the first correction, and you have a recipe to write all the next corrections. One possibility is that you take your student, you give him the problem, and you say, good, compute 2 loops, compute 3 loops, compute 4 loops, right? Okay, problem number 1 is that the number of diagrams here grows like 2n factorial, so it's really hard, okay? It's not just the usual n factorial of QFT. And second is, if you do that, you end up being called by the child protecting services. So what do you do? Well, what you do is that you observe that this is not a new problem. People have been studying the same correlators in a different way, using localization. So it turns out that if you try to study literally the problem of computing these 3-point functions in localization, you can write them starting from the partition function on Z4, constructing a matrix of derivatives. So you see, this is the derivative with respect to tau and tau bar, which is the marginal coupling. This is in the case of super QCD, where you have a marginal coupling. And then in that case, you construct this matrix n by n of derivatives. Then you compute the determinant of this matrix n by n, the determinant of the submatrix n minus 1 times n minus 1, and these 3-point functions are precisely the ratio of these 2 determinants. Now, this is an integrable audience, right? So when you see ratios of determinants, you should start thinking. This is indeed what has happened more than 10 years ago. People started thinking and realized that because of this structure, you can prove that that are essentially 3-point functions, satisfy a total lattice equation. As I said, there is no obvious reason why there should be this structure, but this can be found explicitly, just from the fact that from localization, this is the structure of the 3-point functions. Now, it's an integrable model. That's good. That's good news, right? But how good news is it? There's a big difference between integrable, integrated. I want to get results out of it, okay? So what can we do? How do we find the right solution to the total lattice equation that really reproduces the right physics? Well, again, we use the fact that we know from the existence of the large charge expansion that the structure of the solution is not completely random. You see, the total lattice equation is a differential equation in tau and a difference equation in n. But we know from the structure we found before that the solution we're looking for has to look like this. There's a part that depends on tau, and there's a part that depends on n, but not on tau. And the parts that depend on tau depends on n only, well, either doesn't or linearly. And this structure here is nothing else than the structure that we had found before. The fact that an expansion exists implies that Qn has to look like that. But if you know that, you just plug this form in the total lattice equation, and what you find is that the total lattice equation turns into a pair of coupled Liouville equations and a recurrence equation that you can solve using the one-loop calculation of before. So what you find is that instead of computing loop by loop, order by order, all these corrections, you find a difference equation that contains them all in one go. And you use the one, well, not the really one loop, but the leading order result as a boundary condition for this difference equation. And what you find is that instead of having to compute everything, you get directly the final result. So this log of gamma function here contains by itself all the perturbative expansion resummed. The leading term is the one I showed you before, and all the others will appear just as an expansion in 1 over n of this logarithm. And this is universal. This only depends on alpha, on nothing else, which means that for any superconformal theory with a given A anomaly, we always will have precisely this value. If I put it back in the two-point function that I was computing before, I can write this two-point function as something that depends on tau tau bar times this object here. This is what is forced on us by conformal invariance. And all the physics is just in this little gamma function here. Now, the claim is, since this is the result of a resummation of all the diagrams, this is not just true for theories where you can write the total lattice equation, which is only super QCD, but this is true for any, even non-Lagrangian, superconformal field theory with n equals 2 and the Coulomb branch of dimension 1. It's a super general result. The thing that will change is what happens here, which in the case of SQCD, I can access, and I'll show you now, while in the case of non-Lagrangian theory, is something that is just not physical. Okay. Now, let me say a couple more words about this coefficient here in the case of SQCD. In the case of SQCD, you can go back to your total lattice equation, and as I told you, the total lattice equation contains, well, it's for this A and B of before. C is nothing else than e to the n A plus B, and A in particular satisfies the Liouville equation. The fact that it satisfies the Liouville equation means that you know how to write the general solution. Now you have to figure out what is the good value of these functions f and f tilde that gives you the right physics. Okay, but you need a little bit more input from the physics. You need to know which one of these Liouville solutions to the Liouville equation you want. And the way to do that is to use S-duality now. You need a little bit more physics. So S-duality is a symmetry of SQCD in particular that acts on the coupling, on the marginal coupling. Now, problem. When I say the marginal coupling, I'm cheating, because in n equals 4, there is one marginal coupling. But in n equals 2, the coupling runs. So I will have at least two couplings. One is the one in the ultraviolet, tau. But then, when the theory flows to the infrared, I'm going to have a different coupling, which I will call sigma. And notice, this is a point which was not clear at the beginning. You look at the original Cyber-Witten papers, this is not stressed at all. In fact, there's a very beautiful relation between the two, namely that e to the I pi tau, where tau is UV coupling, is just the modular lambda function evaluated on the infrared coupling sigma. So it's okay, everything is under control, but you have to keep in mind that these are two things. Now, why is this important? Well, it's important because while S-duality acts on sigma, on the infrared coupling, just as you would imagine, just as a rational transformation, if you try to study S-duality in terms of tau, you need to use AGT correspondence, and then you will see that the action of the S-duality is really some funny change of channel in the Liouville theory. So this is complicated, this is simple, but the recursion relation of before comes from localization. In localization, you use tau. So you have a situation where the recursion equations are simple in tau, while S-duality is simple in sigma, which means that you have to choose a frame, either tau frame or sigma frame, bring everything there, do the calculations, and read what is the result. Concretely, the strategy will be to really rewrite everything in terms of sigma and then impose modular invariance, essentially. Okay? The complication in doing that is that you have to, in order to do that, you have to understand how the operators change when you change coordinates on the conformal manifold. In other words, when you change from tau to sigma, how does the operator change? Well, this is something that is also well understood, really, but it requires a moment of thought. But the important story for us is that when you go from tau to sigma, the operator gets a Jacobian. So, and this L is nothing else than that modular lambda function of before. So what happens is that when you want to study these two-point functions, when you pass from tau to sigma, you have to add a power of the Jacobian here. Similarly, in order to be consistent with this transformation property, you observe that e to the a has to transform in a very precise way, namely e to a in terms of sigma gets this Jacobian again, well, it's the square of the Jacobian, times the function in tau. Which means, once you put this inside the Liouville equation, it means that the Liouville equation is actually invariant under a change of coordinates on the conformal manifold. Okay? Good. Now that we know what are the equations we want to solve, which is this one, what we have to figure out is what are the modular properties we want. Okay? So how does the two-point function transform under S-duality? The way to do it is actually quite simple, and it comes back to the observation that the meaning of this operator here is literally an insertion in the quantum field theory, which means that you can obtain it by deriving the log of the partition function. No more, no less. But when you derive the partition function concretely, you observe that in the integrand, you get a term of a square coming down. A is the vacuum modulus. Is literally the VEV that you use in localization all the time. And the vacuum modulus A, we know from Seiberg and Witten, is a modular form of weight 1. So if you have a modular transformation like the one I showed before, A transforms like that. Which means that O has to transform like the square of that, just by consistency. Which means in turn that the two-point function of O with itself has to transform like a non-holomorphic modular form of weight 2n to n. So what is the problem we really want to solve is finding the solution to the Liouville equation that where e to the a is a modular form of weight 2, 2. I spare you the details. You have to take, in truth, it's not even that complicated. You just take a Schwarzian derivative and use the fact that modular forms are very rigid. And there's not much you can do. And what you find is that the solution that satisfies the appropriate boundary condition is given by e to the a being 1 over 16 imaginary square sigma. And at this point, you can go back to the tau frame as you were before. You do the transformation, you put the Jacobian, you use the expansion of the modular lambda function, and you get this form here for this coefficient. Okay, so all of this is very long. There's a lot of math involved, a lot of physics to be understood. So was it worth it? Did we get anything useful out of all these computations? Well, as I told you before, you can compute these things in localization. But when you compute them in localization, localization gives you these ratios of determinants, so they're huge things. And each of these determinants can only be computed numerically, because really what you get is an integral over A, essentially. So what you can do is that you can take this gigantic formula, put them into Mathematica, and get numbers. So localization gives us a numerical result for these things, while we have a little formula, this gamma function, essentially. So how do they compare? Well, in the case of n equals 2 super QCD, the dots are the results from localization, and the continuous lines are the results of the computation I showed you before. There is no fitting whatsoever. There is no free parameter here, nothing. There's just a precise form of the curve I gave you before. That's it. And this, in particular, shows you the first variation of Qn as function of the marginal coupling at different values of the R charge. And you see, once the R charge is essentially 5, it's well, the line is indistinguishable from the numerical results. It's even more striking when instead of looking at as function of imaginary tau affixed n, you look at a function of n for various values of imaginary tau. And you see, you completely cover everything. So this is telling you that that little formula there is really reproducing all the physics that we are expecting. But in fact, when you see something that is so striking, because I can only define that striking, you get greedy, right? You want to think, can I get more? And as I said, the formula we have corresponds to a complete resummation of a perturbative expansion. So in general terms, this cannot be everything, but this is everything that happens around one particular saddle of the path integral. Can we see the other saddles? Well, you know, I use integrability, but it doesn't mean that physics is not an experimental science. So what I can do is a numerical analysis. I take the difference between my prediction and the results that I consider exact from localization, and what I expect is that the difference is exponentially suppressed. Lo and behold, that's literally what happens. You can fit the difference between the exact localization result and the effective field theory, and you got precisely an exponential behavior, literally the one that you had. We have even a physical interpretation for this, but it's time to close. The thing that is important is that once you put back this exponential behavior inside as a correction to our result of before, the agreement with localization is essentially perfect. Good. So time to conclude. Okay, in fact, you can also play with Bootstrap, but I'll save you because I don't have a lot of time. If you have questions, just ask. So the point of today's talk is the following, that if you use this large charge approach, you can actually access CFTs in a perturbative way. And you can actually, well, the idea is to choose a sector, write a controllable effective field theory. And what turns out is that the strongly coupled physics is really subsumed, for the most part, into some semi-classical state, which is really the saddle. And from there, you can compute CFT data, and you have a striking agreement with lattice, with localization. I didn't show large N, you get similar things. And so our point is that with all of this, you can really get precise and testable predictions. Thank you.
Thank you very much for the nice talk. There was already one question a moment ago in the chat, because you showed before the 3D ON sigma model, and you had an expansion in Q. And the question, let me check who it was from Tomeu Fiol. The question was why in that expansion, the large Q expansion, there is no subleading term of order Q. I don't know if...
No, there is. I wasn't clear. I'm sorry. So what I'm showing here, well, the thing I've drawn really is just the leading terms, but the formula itself contains, oh, there you are, subleading term of order q to the minus 1/2. Now the powers are fixed by the structure or the construction, but the important thing is that you have to think of this as an infinite series, really.
No, but I guess he was asking about a linear term, because I see a 3/2, I see a half, a constant, but not...
Ah, okay. Because there's nothing in between.
Yeah, that's right.
Okay, so this is, on the one hand, is an observation, in the sense that you construct the most general effective field theory, and you find that this is how it behaves. There is a deeper reason, which is related to something I said in passing before, which is the fact that this expansion, the way that there is where there's a 2n factorial growth of the diagrams in this theory, and it turns out that this is related precisely to the fact that there's not the Q missing. Notice that this is the reason why this is the number that you can actually compute. And let me just throw one little thing, that this is precisely the same expansion that you get if you put a Rice-Nostrom black hole in ADS. This is literally the expansion you get for the mass as function of the charge.
All right, another quick question from the chat I think we have. from Davide Fioravanti, what is the role or importance of conformality for having integrability? There are things like cyberwritten and the localization that work also without.
I don't know. I mean, the answer is, here we see integrability explicitly, in the sense that you construct these 3-point functions, you observe that you can write them as ratios of determinants, and from there you observe that there is an integrable model behind. You sort of expect it because you know that there's AGT, so you hope for something like that. It actually happens. But as far as I understand, it's an observation.
All right, question from the room. Volodya?
Inside these coefficients here. So C3 halves and C1 half will depend on n. No. It isn't. Okay. Yes and no. So it is strange if you look at it like this. In fact, you have to understand, well, I would have to explain you exactly where everything comes from. But the reason is that all the effective field theories that you write for any n have something in common. And this is the Casimir energy of any effective field theory for any n. And this Casimir energy turns out to be the only thing that is Q independent and n independent. It's actually a very nice thing to compute that in large n, because if it's n independent, it has to appear in large n. And we did it. It took us 3 months to get that number, but it actually comes out also from the large n without any effective field theory.
And very quickly, Alex.
Okay, so this is a question about similarities and differences with large spin expansion, and I wish I could. So the problem is, we all have the feeling that there is something in common. We have the feeling that they should both somehow have something deeper behind. In fact, we're starting really to think of these things as large quantum number expansion in general. There seems to be a fundamental difference in the sense that the nature of the leading term in the two expansion is different. Here, the leading term of the large charge expansion is a big, fat, semi-classical state, while in the large spin expansion, it's rather thought as a big quantum state. This might explain why the two things look different, but I wish I could tell you more.
All right, in view of time, I suggest to thank again Domenico for the nice talk and the answers.
Thank you.